To keep cloud applications running, developers rely on Amazon Elastic Block Store, or EBS, to provide reliable, persistent network storage. But because EBS is a network-attached service, every read and write operation must physically traverse the network fabric, creating a slight, unavoidable latency overhead. For the vast majority of workloads, that overhead is negligible. But when you are engineering high-throughput, mission-critical databases, even a fraction of a millisecond of delay becomes a structural bottleneck. Eliminating that latency requires bypassing the network entirely. You have to pivot to local, physically attached disks. Designing an optimized cloud storage tier requires knowing exactly when to rely on physical hardware, how to decouple network volume performance from capacity, and the strict rules governing multi-node clusters. Misaligning your workload with these storage realities guarantees two outcomes: over-provisioned cloud budgets or catastrophic, irreversible data loss. When absolute maximum performance is required, AWS offers the EC2 Instance Store. These are dedicated hardware NVMe or SSD drives. Unlike EBS, these drives are physically slotted directly into the PCIe arrays of the exact same host server blade that runs your virtual machine. This table details the performance specifications for top-tier i3 and i3en compute instances. Because the physical attachment bypasses the network fabric, the Instance Store can deliver millions of read and write IOPS with minimal latency. That hardware speed carries a severe operational trade-off. Instance Store data is entirely ephemeral. If you stop your EC2 instance, terminate it, or the underlying host motherboard experiences a hardware failure, the data on that local drive is erased permanently. It cannot be recovered because there is no secondary network fabric mirroring the blocks to another location. Consequently, you must never place primary persistent databases or system state files on an Instance Store. The correct use cases for this tier are transient workloads, buffer pools, temporary cache layers, and scratch data processing. Utilizing physical speed safely requires the application layer to manage high-availability replication. Otherwise, the host server blade remains a single point of absolute failure. For data that must survive an instance reboot or termination, we return to the network-attached EBS tier, specifically the general-purpose SSD family. Under the legacy GP2 architecture, storage capacity and performance were strictly coupled. A GP2 volume receives a baseline performance metric of exactly 3 IOPS per gigabyte of provisioned space. This table compares general-purpose SSDs. To reach GP2's maximum IOPS, you must provision 5,334 gigabytes. GP3 resolves this by decoupling performance from size. GP3 scales tiny volumes to 16,000 IOPS, provides a baseline of 3,000 IOPS, and scales throughput up to 1,000 megabytes per second. Migrating legacy infrastructure from GP2 to GP3 immediately optimizes compute budgets and eliminates arbitrary I/O ceilings. General-purpose drives are sufficient for standard workloads, but they cannot guarantee the sustained sub-millisecond latencies required by heavy enterprise databases. That tier of performance requires the provisioned IOPS SSD family, comprising IO1 and IO2 Block Express. IO1 volumes scale up to 16 terabytes and support 64,000 provisioned IOPS when attached to modern Nitro-based instances. When an application exceeds 64,000 IOPS, the architecture must transition to IO2 Block Express. IO2 Block Express is engineered specifically to deliver consistent, true sub-millisecond latency. Returning to the table, look at the provisioned IOPS columns. IO2 Block Express raises the performance ceiling to 256,000 IOPS. It achieves this with a 1,000-to-1 IOPS to gigabyte ratio, allowing extreme I/O velocity on small disks without network bottlenecks. Highly transactional systems like heavy SAP workloads, high-volume Oracle databases, and Microsoft SQL Server setups require this exact performance consistency. Deploying an IO2 volume establishes a rigid performance floor. It acts as an architectural insurance policy that prevents storage bottlenecking during peak transaction events. By default, an EBS volume creates a one-to-one relationship. It can be mounted to exactly one EC2 instance at a time. To build a highly available clustered architecture, you must use the EBS multi-attach feature, which is supported exclusively on the IO1 and IO2 families. Multi-attach allows a single high-performance volume to be concurrently attached and mounted to up to 16 EC2 instances simultaneously. Operating this requires strict constraints. First is the geographic limit. All 16 instances must reside within the exact same availability zone. Second, hardware. Deploy modern Nitro-based instances capable of concurrent bindings. Third, software. Standard file systems like ext4 will cause simultaneous write collisions and data corruption. You must configure a cluster-aware file system, like GFS2, to safely queue and negotiate block writes across the entire cluster. Adhering to these constraints allows engineering teams to construct a resilient database cluster that can fail over seamlessly, completely avoiding data synchronization delays. To review, local instance stores bypass the network to provide absolute hardware speed, but demand application-level fault tolerance to handle rapid data volatility. On the network layer, modern architectures like GP3 and IO2 Block Express eliminate legacy provisioning traps by completely decoupling I/O throughput from physical gigabyte limits. And when clustering nodes, EBS multi-attach scales access across 16 instances, provided they share the same availability zone and run a cluster-aware file system. With these strict block storage limits defined, the next architectural challenge emerges. How do you secure this volume data in flight? And how do you mount a shared storage layer across entirely different availability zones at the same time? Next module, we will answer that by exploring EBS key management service encryption mechanics and the distributed architecture of the Amazon Elastic File System.